Hi everyone. In the last lecture, we have discussed the spectral theorem for self-adjoint operators. Today, we'll look at some examples of this spectral theorem. So, let us quickly recall the spectral theorem. If T is self-adjoint bounded operator, we have shown that there exists a family of orthogonal projections E lambda satisfying the following conditions. That is, they are monotonic. That is, whenever lambda 1 less than or equal to lambda 2, then E lambda 1 less than or equal to E lambda 2, and E lambdas are supported on the spectrum of T. That means E lambda equal to 0 when lambda is strictly less than the lower numerical bound, and E lambda is identity when lambda is bigger than or equal to the upper numerical bound. And if A commute with T, then each projection E lambda commute with A, and it is also right continuous. That means if we take E lambdas where lambda is bigger than lambda naught, then E lambda x converts to E lambda naught x for every x in H, and T can be represented using this integral T equal to integral a to b lambda dE lambda, and we have discussed what is the meaning of this integral, and a is less than or equal to small mt and b is bigger than or equal to capital MT. And we have shown that if you take E lambda equals to orthogonal position onto null space of T lambda plus, where T lambda is T minus lambda I and T lambda plus is nothing but mod T lambda plus T lambda by 2, then this E lambda satisfies all the required conditions. Now let us look at a few examples to illustrate the spectral theorem. So let us start with a 2 by 2 matrix. So let us take alpha beta to be real numbers with alpha less than beta. Define T from C2 into C2 by T of xy equal to alpha x beta y, where xy is coming from C. That means the matrix of T with respect to the standard orthogonal basis of C2 is nothing but 2 by 2 diagonal matrix with diagonal entries as alpha and beta. Okay. Now in this case we can easily find out that small m suffix t is alpha, capital M suffix t is nothing but beta. So let us take a less than alpha and b bigger than or equal to beta. We want to look at the spectral family generated by T. So for that we want to let us take lambda in R, then T minus lambda I. Let us write this as a matrix form only. This is alpha minus lambda 0 0 beta minus lambda. Then if you look at mod T lambda plus T lambda by 2, that is T lambda plus, this is nothing but mod alpha minus beta plus, mod alpha minus lambda plus alpha minus lambda by 2 0 0, this is mod beta minus lambda plus beta minus lambda by 2. Okay, now E lambda is nothing but orthogonal position onto null space of T lambda plus. Now here whenever if you take alpha less than or equal to lambda less than beta, then we can show that T lambda plus, when alpha less than lambda, then alpha minus lambda is negative. So in that case you will get this to be 0 0 0, and this one is nothing but beta minus lambda. So in this case null space of T lambda plus is nothing but span of E1. So let us say E1 is 1 0 and E2 is 0 1. So when if beta less than or equal to lambda, then we have t lambda plus lambda is bigger than beta, means beta minus lambda is negative. In this case you will get the whole operator to be 0 0 0 0. So null space of t lambda plus is the full space C2. So using this we can write down the spectral projection or spectral family generated by E lambda. E lambda is nothing but when lambda less than a, it is 0, because when lambda less than empty it is 0, and when lambda less than beta, we have shown this is E lambda to be null space of t lambda plus is span E1. So we have to look at projection onto span E1. So let us call this as P1, where P1 is projection onto span E1. So this will write E1, this is span E1. And next one is identity when beta bigger than or equal to lambda bigger than or equal to beta. So beta less than lambda. Okay, these are E lambdas. Now we want to find integral a to b lambda d E lambda using these E lambdas. Okay, here, so let us try to look at this as, let us say that this is A, this is B, okay, so this is A, so this is A and this is B here. Now we have to look at a partition here, so let us look at a partition around. So let me take this is alpha, this is beta, so this is A, this is B. Okay, now let us look at a partition where alpha is a midpoint. Okay, and okay, so let us consider summation j equal to 1 to n lambda j hat E lambda j minus E lambda j minus 1. So here we can actually lambda j hat we can take A and B, remaining in between we can take some other also. So here if you look at if lambda is bigger than or equal to A, E lambda and EA are same. If you take any lambda bigger than A, then E lambda EA are same. So the first one you will get as, we can take lambda 1 hat as A into E alpha EA minus E alpha minus EA plus lambda 2 hat E lambda 2 minus E lambda 1. They are all bigger than A. So on last you will get beta times E beta minus E beta minus 0, because that is smaller than beta. this is E alpha. So it is actually let us say this is lambda 1. So here you will get E lambda 1 and this is lambda naught is A. So EA you will get 0 because it is less than alpha. The first one you will get as A into E lambda 1, that is P1, and remaining everything you will get 0 because E lambda 2 and E lambda 1 are same, and finally you get beta times. So this is alpha we have to take because alpha is the midpoint of the rectangle. Now this is E beta is identity I minus E beta minus 0, that is lambda, is a lambda which is bigger than A, so you will get P1. So you will get this as alpha P1 plus beta P2, where P2 is I minus P1. In fact, this is the matrix that we started with. Okay, so that means if you look at this kind of finite linear combination of operators, then they approximate the original operator. That means we can easily show that T minus summation j equal to 1 to n lambda j E lambda j minus E lambda j minus 1. So this goes to 0 and then goes to infinity. Okay, so therefore we can say that T is nothing but integral a to b lambda d lambda. So we got this as a p1 plus alpha p1 plus beta p2. Okay, let us look at one more example. Let us define T from C3 into C3 by T of x y z as alpha x beta y gamma z for all x y z in C. So here alpha, beta, gamma are real numbers with alpha less than beta less than gamma. In fact, we can take less than or equals to also. So T is nothing but with respect to standard orthogonal basis of C3. So you will get alpha, beta, gamma, remaining 0. Okay, now let us try to approximate T by the projections. We want to look at E lambdas as in the earlier case. Here MT, small mt is alpha, so capital MT is gamma. Now let us take A less than alpha, B bigger than or equal to gamma. Now we want to take a partition for AB and do the same approximation that we did earlier. So in this case, let us try to find what is E lambda. This is 0 when lambda is less than alpha. Now we want to see when lambda is between alpha and beta. So alpha less than lambda less than beta. Like the earlier case, it is same P1 we will get projection onto span E1. And when beta is less than or equal to lambda less than gamma, so when there are two suppose alpha, beta and gamma, so we have like this. So E lambda between alpha and beta we have decided. When lambda is somewhere here, now E lambda will be containing eigenspaces corresponding to alpha and beta in projections onto the corresponding eigenspaces. So that is nothing but you will get P1 plus P2, and when gamma is bigger than alpha, lambda is bigger than gamma, you will get identity. So when gamma is, so your Pj is projection onto Ej, j equal to 1, 2, 3. Identity is nothing but P1 plus P2 plus P3, that is identity. Okay. Because here when let me explain, when lambda is bigger than beta, bigger than or equal to beta, now t lambda plus, you will get, like earlier case we got here 0 0 like this, you will get here 0 0 0 0 0 0 0 0, we will get gamma minus lambda. We can take a partition, we can take A here and B here and take a partition lambda not equal to A and less than lambda 1, less than lambda 2, so on, and lambda j minus 1 is less than beta less than lambda j, and so on, lambda n minus 1 less than gamma less than lambda n, that is B. Now if you look at the summation, lambda 1 hat, so we can take lambda 1 hat to be, so lambda 1 hat e lambda 1 minus e lambda naught plus so on. Here you will get lambda j hat e lambda j minus e lambda j minus 1, so on. The last one is lambda n hat e lambda n minus e lambda n minus 1. You will get like this. This is, I am taking lambda 1 hat to be alpha and e lambda 1 is P1 and e lambda naught is 0, plus if you take any partition in between, any subinterval, take the corresponding e lambda I minus 1, e lambda I minus e lambda I minus 1, they are same because lambda I minus 1 is bigger than alpha, so everything we get same between alpha and beta, so we can get everything 0, and lambda j hat, it is beta into e lambda j, you will get P1 plus P2, and lambda j minus 1 is less than beta, you will get minus P1 plus so on. Lambda n hat is nothing but B, sorry, lambda n hat is gamma, and this is nothing but identity minus P1 plus P2, so this is identity minus P1 plus P2 will get, and this is nothing but alpha P1, you will get alpha P1 plus beta P2 plus gamma P3. This is one approximation, and in fact this is the original operator. So in this way we can actually look at t minus gamma of t minus summation j equal to 1 to n lambda j hat e lambda j minus e lambda j minus 1 goes to 0 as n tends to infinity. That means t is nothing but integral lambda d lambda. So we can say that t is nothing but integral lambda d lambda is nothing but from a to b, this is alpha p1 plus beta p2 plus gamma p3, this is nothing but t. Okay, so let us take T to be self-adjoint and compact operator. So then we know that T can be written as summation lambda j pj j equal to 1 to infinity, where pj is nothing but orthogonal projection onto null space of T minus lambda j, and this lambda j goes to 0 as j going to infinity, provided lambda j's are infinite. And we know that the operators on the right hand side converges to T in the operator now. Now let us look at what are the E lambdas and how to integrate T with respect to those E lambdas. So as in the earlier case, we can represent this as matrix lambda with it's a diagonal matrix with diagonal entries as lambda 1, lambda 2, lambda 3. So with respect to the orthonormal set, the eigenspace of with respect to the eigenvectors, we can represent the operator in this way. So in this case, when we take lambda bigger than lambda j, so we can, as in the earlier case, we can actually show that E lambda is nothing but summation over j, such that lambda j less than or equal to lambda, corresponding pj you will get when lambda less than 0, summation j lambda j less than or equal to lambda pj plus p naught when lambda bigger than or equal to 0. P naught is orthogonal projection onto null space of T. So we will get P naught whenever 0 is an eigenvalue for the operator. Okay. So this is a projection which we can write down using the earlier two examples. Whenever lambda is bigger than some lambda j, the corresponding, we have to add all the orthogonal projections onto the corresponding eigenspaces, then that will give E lambda. So as in the earlier case, if you look at E lambda j minus E lambda j minus 1, this is nothing but E lambda j is summation j equal to 1 to summation over j, so that it is pj up to lambda whenever lambda j less than or equal to lambda, and E lambda j is similar to that, but lambda j minus 1 less than or equal to lambda. So the difference of these two projections is nothing but pj. So hence we can actually write down summation j equal to 1 to n lambda j E lambda j minus E lambda j minus 1. This is nothing but summation j equal to 1 to n lambda j E lambda j minus this one, we will get projection onto null space of T minus lambda j. Here we can take lambda j had to be lambda j's which are exactly the eigenvalues of T. Now we know that this goes to 0, so hence if you look at T minus summation j equal to 1 to n lambda j pj, so this is nothing but this, we can show that because T equal to summation lambda n pn, n equal to 1 to infinity, so this we can show that is then equal to mod n plus 1, which goes to 0 as n tends to infinity. That means, so T is nothing but integral a to b lambda d lambda, in this case that is T, it is nothing but summation j equal to 1 to infinity lambda j pj. So this is the representation of T. Okay. Let us look at the continuous version of this example, namely the multiplication operator. Let us take phi of t equal to t when t is in 0 1. Define the multiplication operator from L to 0 1 into L to 0 1 by m phi at f t is phi of t f of t, that is t times f of t for all f in L2 0 1. Okay, now we want to look at E lambdas for m phi. So we can easily show that m phi minus lambda I is m phi minus lambda multiplication by the constant function 1. So this is nothing but m phi minus lambda into 1. So also we can show that mod m phi minus lambda into 1 is m of mod phi minus lambda 1. So therefore we can actually show that m phi lambda plus is nothing but m phi lambda plus phi lambda is nothing but t minus lambda. That means if you are able to find phi lambda plus, then we can get m phi lambda plus. So we can actually get this as, so whenever lambda is bigger than t, then t minus lambda is negative. In that case, so you will get 0 when t is less than or equal to lambda, and you will get t minus lambda when lambda is smaller than t. Okay, so in this case we can actually write E lambda. So now if you look at null space of m phi lambda plus, that is nothing but range of E lambda. So we can easily find E lambda f at t is f of t when t less than or equal to lambda, 0 otherwise. This we can easily calculate using the same procedure that we have done earlier. Now in this case, this we can write as multiplication operator induced by the characteristic function from 0 to lambda. That means the spectral family generated by t in this case is nothing but multiplication operator induced by the characteristic function supported on 0 comma lambda. Now if you look at the lower numerical bound for this operator, so this is 0, and the upper numerical bound this is 1. By definition we can show this. And if you take any partition from 0 to 1, okay, so if let us take lambda naught is 0, this is lambda less than lambda 1, lambda 2, so on less than lambda n equal to 1. If you look at E lambda j minus E lambda j minus 1, because we want to look at lambda j hat multiplied by these operators from j equal to 1 to n. This is summation j equal to 1 to n lambda j hat E lambda j minus E lambda j minus 1. E lambda j is the multiplication operator induced by the characteristic function supported on the closed interval 0 to lambda j. Other one is up to lambda j minus 1. So if you look at the difference, you will get this as multiplication operator induced by the characteristic function supported on lambda j minus 1 lambda j. Okay, so we can understand this if you draw the graph of the function. Okay, so let us look at f of t equal to t. So let us take So this is 0, this is 1. So we are taking a partition. This is lambda 1, lambda 2. So this is lambda n, and 0 is lambda 0. In fact, here we can take lambda 0 little bit. So we have to take a less than 0. So here a. So here for lambda 1 we get partition like this, rectangle like this. For lambda 2, for lambda n we will get like this. So here what is happening is that we are approximating the function phi of t equal to t using these rectangles or step functions, and correspondingly we are approximating the given multiplication operator induced by phi with the multiplication operators supported on these subintervals. So that means in the function level we are approximating the function by simple functions or step functions. At the operator level you are approximating the original operator by sequence of multiplication operators supported on the subintervals uh, which are which approximate the given function. So that's what happening here, and we know that if you look at approximation like this, they approximate the original function phi. So we can actually show that this norm of m phi minus summation j equal to 1 to lambda j at a lambda j minus a lambda j minus 1 this goes to 0 as n tends to infinity. Okay, so this is one important example for writing down the spectral representation of a self-adjoint operator. So we'll see some more important properties at a later stage. I'll stop here. Thank you very much.